All right, so today I'm going to talk about plate curves and load lines. And many of you have probably seen these before and may know how to use them, but if you don't, this is going to be a video for you. And even if you do, maybe you'll get something out of this video as well. And we're going to start sort of with the basics and then sort of work our way up all the way to different types of output stages. So we're going to start with just a signal stage here with the 12AU7, but we'll work our way up to push-pull AB1 output stages. So hopefully the video won't drag on too long, but I'll try and be as quick as I can. So let's get started. First of all, let's remember what sort of an amplifier looks like, so we know sort of what the context is here. And you can kind of see here that this is like an output stage. And so the voltages that we're going to be talking about and the currents that we're going to be talking about are happening here at this point. It's part of a greater system. It's half of a voltage divider, a voltage and current divider here. And so when we see for instance, voltage on the plate swing up, but then the current swing down, just remember that the reason it's doing that is because it's part of a divider here. And since we're starting with a signal stage, let's just keep in mind that with a signal, the tube is part of a greater system as well. And so you've got a supply voltage up here, you've got your load resistance, then down here you have your plate, you've got your grid, your cathode, probably a cathode resistor to set your operating point. Right here you're going to have a grid stopper. You're going to have a grid leak like this. You're going to have potentially a capacitor from the previous stage where the signal's coming in, and you're going to have a capacitor out, and then the next stage that you're driving is going to have some non-infinity resistance, and so we can call that, what I guess the load. This is the load resistor, but this would be the load of the next stage. I don't know what to put on there, but anyway, just remember that the voltages and currents we're talking about are happening here, and so that's the broader context here of the load lines that we're going to be looking at. And so you've probably seen these load lines in the data sheets of the various tubes that you've looked at, and they might look a little mysterious, but they've designed these load lines to be very easy to use and helpful. And there's a lot of data in here, as you're going to see. And so the reason they include these is because you can give a bunch of specs, for maximum ratings and maximum current and sort of average operating point, stuff like that. But those are like snapshots of sort of the bigger picture of what the tube can do and is doing. And this is a much more complete picture. And so, when you look in the data sheet and it says the gain of the tube or the mu, well, that's here. Or when you look in the data sheet and it tells you what the transconductance of the tube is, that's here as well. Also, just general sort of like the plate resistance, that's here also. And so also the distortion, when it specs sort of a distortion or whatever, you can see that the distortion is right here. So that's why these are so useful and why they're so cool and why you should understand them. And so to start with, the first thing we need to do is we need to sort of see what's going on here. So over here on the left, we have current, and this is in milliamps. And so it's always going to be in milliamps for tubes because tubes are high voltage, low current devices. And then down here, we have our voltage here. So that's what's happening. In the middle here are various operating points of voltages and currents. And you'll see these lines coming through here. These lines are differential voltage between the grid and the cathode. And so what this is saying here is that if you're on this line, the difference in voltage between your grid and your cathode is -6 volts, which means that the grid is 6 volts lower in voltage than the cathode. And you can see it's got 0, 2, 4, 6, 8, 10 all the way up here. And so you can basically find any point that this tube can operate in right here. And so another thing you should notice is that there's voltages and currents here, and you can see there's like a large area up here that's unused, and over here that's unused. These are areas that the tube cannot operate in. Over here it cannot operate there because it can't swing positive. The grid cannot swing positive of the cathode very easily, and when it does, the grid will conduct and heat up and potentially damage the tube. Now that's not always the case. Some tubes are designed to operate in this area, but it also requires sort of a specialized driver stage. So for all useful purposes today, this area is inaccessible to us, the positive of 0 volts. And up here, this is beyond the dissipation rating of the tube. These potentially just continue on up here like this, but you know, or maybe you don't know, but power, that's in watts, is equal to volts times amps. And so you'll notice on our curves here that that's exactly what we have. We've got volts and we've got amps. And so the 12AU7 has a maximum dissipation of 2.75 watts. So it's 2.75 watts equals V times I. And so you'll notice that for each one of these lines, there's a point at which it's going to intersect a voltage and a current that is 2.75 watts. And so you can redraw this pretty easily because it's volt times amps. You can take either of these variables here and you can divide power by either one. And so this time we're just going to go ahead and divide volts, I think. Yeah, we're going to divide volts because that makes it easy. So we'll cross this out and divide by volts over here, and we get power divided by volts equals current. And so we know that our current we're shooting for is 2.75 watts, and so we end up with 2.75 watts divided by our voltage is going to equal our current. And the reason this is important is because we need to figure out where the maximum dissipation point for our tube is. And so it's easy enough to do this. We'll pick a voltage right here. We're just going to pick a voltage. We're going to pick 120. We're going to do 2.75 divided by 120 equals, look at that, so we got 22.9 milliamps. Let's mark this in red. 22.9. So here on the 120, the maximum dissipation is here, okay? And so what I'm going to do is I'm just going to go through each one of these voltages and I'm going to mark out the max dissipation. All right, so now that we've got that done, now a lot of load lines will actually come with this line already drawn, but we're going to draw it like this, and you can kind of see where it's going and connect the dots here. And so that is the maximum dissipation of the tube. That's why you can't use this area up here. And so we're going to now look at sort of the various DC operating points that we can pick. Now, usually a driver stage like this is going to be loaded by a resistance. You can do choke loaded, but generally speaking, you load it with a resistance, and so that means that it can only the voltage can only swing up to the supply voltage that you have, and so we'll have to keep that in mind when picking a DC operating point. You'll also notice that as the tube swings here through this area, it doesn't swing equally through the voltage as you increase and decrease the grid voltage. And so it doesn't swing equally through the plate voltage. That's distortion. That's where the distortion comes from, that your output waveform, your voltage waveform, is not going to look like your input voltage waveform for that reason. In any case, this is all laid out really easily so you can see. Now, if we just, let's just willy-nilly, I guess, lay a line. I've got these lines I cut out. Let's just lay a line across here and see what we can come up with. So let's assume that our supply voltage is going to be somewhere in the 350 range. I think that's a reasonable assumption. Maybe it'll be a little bit lower than that, but a lot of amps you'd use this in, that would be a sort of a normal range. And so what we do is we'll just find that up here, which is right about there, and we'll keep our finger there. And then what we can do is we can kind of move this line. Now these curves are set up so that the load line is flat, and I'm going to tell you what that means in a minute here. They're straight. So, all right, so let's just put it right here for now. And we're going to look at this, and we're going to say, look, that's 17 milliamps over here, and we're at, what are we at? 350 volts. So we can find what this load line represents in a resistance value by dividing the voltage by the current here. All right, and so you can see we've come up with a load line that represents 20K. Now the cool thing about this, so that's, that's a pretty typical load for a 12AU7, a 20K load resistor. So you can see why somebody would use that. Now, keeping in mind, I'll explain more in a second, but let's just assume that the load resistance plus the load resistance plus the next stage add up to 20K. So that you can see this is how you're going to be swinging through. And so now it's time to pick a DC operating point. And usually you want to pick a DC operating point. Now you have to keep in mind the output voltage you want to swing, because you can see that this load line swings through about 90 right here, all the way up to our supply, which it actually won't reach that, but it will, it'll get up there. But it swings all the way up here, so there's 0 volts. And so if we were to pick, for instance, a 2-volt operating point, it could only symmetrically swing down 2 volts, or up 2 volts, I guess, if you want to think about it like that, to here. So let's say we picked that as our operating point. We would only get a swing from here to here, and then up again to here. So we get, what, 90 to 140 to 160 or whatever. But that's a pretty linear area. You can see that the voltage difference between here and here is pretty similar to here and here. However, if your next stage, for instance, is a power output tube, and it needs something like, 100 volts or something, peak to clip it, then you're stuck trying to get more swing out of your tube, and so you're into a less linear zone. And so you could come up here, for instance, and set your operating point at negative 4 volts, and then you could swing, from 160 down to 90 there, and you could swing up to 210 or something up here. And so you can see now that the output swing is going to be greater, but you can also see that this is the second order distortion coming in, where one side of the waveform is doesn't swing quite as far as the other in voltage. And so you have a trade-off here between sort of the maximum output swing you can swing. And so here's a cool thing about this load line. The slope for our 20K is always the same angle. And so now, if we keep the same angle, it doesn't matter what we do. Like if we divided this voltage by this current, we'd get 20K. And if we divide this voltage by this current, we get 20K. And so as long as we don't mess up the slope of our load line, it's always 20K. And so that's pretty cool. So anyway, let's pick a DC operating point. It can be anywhere in here, but generally speaking, for maximum output swing, you would pick half supply voltage or whatever, or you'd pick halfway in between. So let's just say 350 and right here again, and so somewhere in the middle where you could go up 1, 2, 3, 4, and you could go down 1, 2, 3, 4, something like that. And so you're looking at an operating point. I'm gonna put this is our operating point right here. And you'll see why I'll do that in a minute. There's our operating point. So it's 350 up to and 17 milliamps there. So now keep in mind, this is what you should look for. So this is your operating point. You're at -8 volts between the grid and the cathode. You're going to have 200 volts on the plate about. And this is, you're going to be able to swing, if you give it if you put your voltage in, and it's plus or minus, 8, if it's 16 volts peak to peak, so it can go 8 down and 8 up, you're going to end up with your swing being something like this. So here's your voltage swing. You'll also see that you're swinging current over here, and so you're swinging between right here and somewhere down in here. And so you can see now that if you were to decrease the load, you would change the angle. And what you do is you would decrease the voltage that you can swing, but you would increase the current that you can swing. And so it makes a lot of sense now when you load down your circuit why it decreases the output. It's because it requires more current. And so this is another interesting thing that I guess we should talk about at this point. When I was trying to say earlier that the load lines here represent a lot of different metrics, the gain of the tube, the intrinsic gain of the tube, is its gain into an infinite impedance. And so an infinite impedance looks like this. You flatten your load line out. And so then you can see that if you go up, let's say 2 volts, you swing between here and here. And so you can literally just do that math and do like voltage, voltage out divided by voltage in, and it will give you the gain of the tube. In fact, I'll do that right now. So what we got here is I just did it between here and here because those were convenient. And I looked here and I said, this is 2 volts difference here. So 2 volts on the grid equals the difference between 120 and 160. So 60, 50, 40, 40 volts. And so what you do is you go 40, this is easy obviously, do it in your head, divided by 2, 20. And so you can see that this 1287 has a mu of 20. And so if you look in the data sheet, well, that's not exactly correct maybe, but every tube is different, and these are obviously curves that have been taken off somebody's tube in somebody's curve tracer. And so, but you can definitely see that's what we're getting here on this. We're getting a voltage gain where 2 volts nets us 40 volts, right? So that's the gain. Now you can see as you load the tube back to our operating point here, the gain decreases. So now we can look and we can see the difference between 2 volts here is going to end up being something like this. So 2 volts will be now, I don't know, it's less, it'll be, let's take 10 off of that. Maybe it's 30 now, and so it'll be, 15. So now our gain's down to 15 with this load line. So you can see now how the gain changes with the loading, and the more you load it, your voltage gain goes away. But now all of a sudden you're swinging through lots of current. But you're also getting into a very nonlinear part of the tube where it swings up a ton and swings down and gets all squishy down here. That's not a technical term. Anyway, so that's the mu, or the intrinsic gain of the tube. So that's fun. So the opposite of that, or it's the same in a different way, is the transconductance. So the transconductance of a tube is if the line is right up and down like this, and you can see how much current you gain. This depends on your operating point, obviously, but how much current you gain for input voltage. So transconductance is current out divided by voltage in. So we'll do that really quick. About 4 milliamps for 2 volts. So that's, we're getting about 2 milliamps per volt. So that's our transconductance. 2 milliamps per volt. So, so interesting now you understand what transconductance is. So you got transconductance, you got your gain. You should also keep in mind that these curves, a pure voltage source, something that has, so yeah, let's get into this now. So now we have plate impedance, something about plate impedance. And so you can see what the plate impedance is here. So if I go up back to our previous curve right here, it actually doesn't matter where the curve is, whatever, but so to ask what the impedance is to ask how much current you have to supply to change the voltage of the plate 1 volt. And so what you look at is, let's say you've got a -8 between your cathode and your grid. And so let's say I wanted to change the plate voltage by 40 volts here. Okay, so I need to change the current now from here down to here. And so that's a change of, what is this? We'll just call this 11. And down here is 6. So the difference between 6 and 11, 5, of course. And so if we want to change the plate by 40 volts, we need to supply 5 milliamps. And so then what we do is we go back to Ohm's law. 40 volts equals 5 milliamps times our plate resistance here. And so we can take this and remove over here, divided by 5 milliamps. Yeah, take it out of here. And we'll find our plate impedance this way. So it's going to be 40 divided by 0.005 equals. And so you can see we've come up with a plate impedance of 8K. And I think that's pretty typical for a 12 AU7. So our plate, yeah, so our R, I guess it's called RA, 8K. And so, yeah, so we found our plate impedance there. Now, a plate impedance is going to change depending on the angle of these grid lines. A perfect voltage source would require infinity current to change the voltage. In other words, it could sink or source endless current and the voltage would never move. And so the lines would be straight up and down for a perfect voltage source. Those don't exist. Regulators do a good job over a limited range of approximating them, voltage regulators. And then the current source is the opposite. So the current source would have an infinity output impedance and would supply the same amount of current into any load. And all of the lines here, the grid lines, would be straight across like this. And it wouldn't have a voltage gain so much anymore as it would have a pure transconductance. And so we'll get to that because you can see that this triode is sort of halfway between what you would call a voltage source and a current source. The lines kind of just go through like this. And later on, we're going to look at a pentode. when we do Class A, B load lines. And when we look at the pentode, you'll notice that the lines go up and then they come basically straight across. And so when you hear people say a pentode is like a current source or it has a very high plate impedance, this is what they're talking about. The question is, how much current do you have to put into the plate to change the plate by whatever voltage? So that is the question. Anyway, so here we are back at our load line here. We've got our operating point. You can see we can move our operating point anywhere we want along this load line, and we can change the angle of our load line by changing our load resistance. Now remember that of a driver stage, the load resistance is not just it's not just the load resistor. So like I said, like I was showing before, you come in, you've got your grid leak, you've got your grid, you've got your plate, cathode here. We forgot the cathode resistor, but that's not important here. We're going to have a load resistor, a supply voltage, and output, and then we're going to come over here. So this is important. We have a DC operating point that's set by this resistor alone, and that's how we get our DC operating point here. But the load up here, which is usually set by the grid leak resistor of the next stage, which would look like this. That's the grid stopper. So here's, let's say, our next stage right here, okay? And this is probably an output stage, so let's put a transformer on it, like this. Your speaker will go over there. And so the AC operating point, of course, has to go through this cap, because cap is an AC short at audio frequencies, or it should be, if your design is right. And so when the AC signal swings, it doesn't just swing here, it also swings this way. And so what happens to your load line here is it begins to, like I said, begins to tilt. And so if this value here is quite low, which it might need to be depending on your output tube, the DC operating point will stay the same here, but the AC operating point will start to shift this way the more you load it down. And you can see that a little bit of a shift is not so bad. Still pretty linear, not so bad right there. But if you load it down a ton, you can end up doing something like that. And even though your DC operating point hasn't changed, your tube is now in distortion land and not swinging nearly the voltage. You know, you've swung down to where put my pen. You know, to what here, from here to here now, and so you can see how loading down the stage has affected it. Right. So I hope that has demystified these load lines here. So we're going to move on to power stages. We're going to start with a Class A output stage, and it's a little bit different because you load those with an inductance, which is the output transformer, instead of a resistance, and so they're a little bit different. Okay, now we're going to look at we're going to start with a Class A output stage here. And we're going to use the load lines for a 6L6. And so just a reminder, this is what an output stage looks like. And the plate voltage and currents are measured at this point. So they're part of a resistive divider here, right? Okay. So the first thing we're going to do, once again, is we're going to mark off our maximum dissipation line. And this tube dissipates a maximum of 30 watts. And so I'm going to real quick just do that. All right, so you can see, just like before, our max dissipation line is a curve, and it does this. That is 30 watts. We also have a maximum plate voltage for the 6L6 that you don't want to exceed. It's 500 volts, so that's right up in here. Now that's the DC operating point. It can swing AC above that, so don't worry about that. So we know that okay, so here's the difference between the resistive loaded and the inductively loaded stages. An inductively loaded stage, your supply voltage is your operating point, and because an inductor will apply voltage to try and resist the change in current, the voltage will swing above the supply voltage, which is a pretty neat trick, and is why tube amplifiers are a great match with output transformers, in that you can swing right on up above, and so you don't have to have a supply voltage of 800 or 900 volts, because your DC operating point can be fairly low. I mean, 400 odd volts, 500 volts is not that low, but I mean, it's much better than trying to get a supply up here, like with a resistive load or whatever, and then having to sort of swing up and down from there. You can start up here. But anyway, so just that's how output transformers work. They're inductive, and they will allow you to swing above. And so whatever your supply voltage is, there'll be a little bit of DCR in the transformer primary, so your voltage will maybe be 5 or 10 volts below, probably less than that, probably 5 volts below supply voltage, but for all practical intents and purposes, it's going to be your supply voltage. But because we're creating a Class A stage here, we don't want the tube to clip asymmetrically, and so we want actually our operating point to be somewhere in this region, because we would like the tube to be able to swing, because it's going to clip at 0 volts, obviously. It's also going to clip over here. Now you can't see these on this, but these just keep going like this, you know, and they get more and more squished over here. So we want to be able to swing up and down fairly equally, and it will soft clip up here as it reaches sort of a maximum voltage, and it'll round off. And it'll hard clip down here when it gets to 0 volts if your driver stage is not specifically designed to drive it the grid positive. And so we want our swing to be in here somewhere. And so let's say if we put it here, we've got 1, 2, 3, 4 here, and we could go 1, 2, 3, 4. And so that's not so bad. Or we could go up to here and we go 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Now you're getting some distortion there, because look, you swing from here to here, that's a lot more voltage than you're swinging from here to here. And so you can see that you have a trade-off here between power output and linearity. I should talk about power output, because what we're trying to do with an output stage is create power, right? And with the driver stage, it's less about power and more about voltage gain and output impedance. I mean, it's still about power, but with an output stage, you're trying to actually, you know, drive a speaker with it or something like that. And so the way you develop power is, remember that power is a volt amp. And so you want to swing through as much voltage as you can, but you also want to swing through as much current as you can. So if you only were swinging through voltage, that would mean your load was infinity. Remember, like before, I should be using my load line. So if your load is infinity, your load line looks like this, and no power is generated this way, because remember, power is a volt amp. And so if your load is 0, you're going to swing current through it, but your voltage is not going to change at all. And so you don't develop any power that way either. And so the way you develop power is by swinging through voltage and current. And you do that by having a finite load resistance. And that's going to be dictated by the ratio of your output transformer. And so in this case, we're doing a single-ended Class A amplifier here. And so the output transformer might be, for instance, well, let's just see what it is. Let's pick an operating point. We'll just say it's here with a Class A operating point. You want to bias it close to maximum dissipation, and you want to swing through as much voltage and current as you can. So I think this looks like a pretty reasonable operating point. And so we're ending up up here at well, we won't get up to 700. So let's see where we get. So we can go this many volts down. We're going to go 32 down and 32 up. So 1, 2, 3, 4. 1, 2, 3, 4. So this is our swing. We're swinging. What is this? Halfway between 490 and 560. This is probably 520 or something like that. 510. We'll just say 520. All right, and we're going to swing down here to 150-ish, right? And we're also going to be swinging through. You can see we're down here to 30 milliamps, I guess. 30. And we're going to go all the way on up to, let's see, 115 milliamps. Right. That's good to know. Also, now we can figure out exactly what the primary impedance of our output transformer should be, because we can see here we're going from 700 volts and we're going all the way up through, looks like 150 milliamps. And so you can see that our output transformer primary should be in the 4 to 5K range. I'm getting 4.666. So a 4.5 or a 5K output transformer, and you can see that our DC operating point is about 360 volts, and our grid is at about -32. And so if we built this, we would want a supply voltage of 360 volts, which is, it's reasonable supply voltage. We'd want to set the grid -32. We want output transformer to be in the 4.5K range. And we can see exactly the current and voltage that we'll swing through here. And so, there's your output power. And so we can calculate the output power pretty easily. If we assume that the wave is actually a sinusoidal wave, then all we have to do is do the plate-to-plate voltage, figure out what that, the plate-to-plate, the peak-to-peak voltage, and then divide that by 2.83 to get the RMS voltage swing. And then we do the peak-to-peak current swing, and we divide that by 2.83 to get the RMS current swing. And we multiply those together, and that gives us, a ballpark of the power we can expect from this Class A single-ended output stage. And so I'll do that really quick so we can see what that is. Okay, so you can see that we have we're swinging 370 volts peak to peak, and that's 130 odd volts RMS. And we're swinging 85 milliamps peak to peak, which is 30 milliamps RMS. And so now, if we multiply those together, because remember power is a volt amp, we get about 4 watts. 4 watts. So, now, I neglected to mention this in the beginning. This is a triode strapped 6L6. You can see that it's triode because remember how the grid curves are kind of halfway between what we'd expect for a perfect voltage source and a perfect current source? That's what triode curves look like. And so, congratulations, you've made a little 4-watt amplifier. You can also, this is interesting, like just with before, you can figure out the plate impedance of this stage just by looking at how much current you have to drop in to the plate to change it by, let's say, so it's changed even by 70 volts here, and you can see we're doing from here to here. This is 90 minus 40, so we got here we go. So in order to change the plate by 90 volts, we have to put in 50 milliamps. So we're going to do 90 divided by 50. 0.05 is 50 milliamps. And so we can see that the plate impedance of our triode strapped 6L6 is about 1.8K. And that's pretty typical for a triode strapped pentode. I think EL34s are a little bit lower than that. 6V6 is a little bit higher than that. But that's pretty typical. We can also see what the gain of our stage is. All we have to do is look at the voltage we put into the grid and the voltage we get out at the plate to see what the gain. Obviously the gain, the mu of the tube is going to be with that theoretic infinity load line. Since we've tilted ours, our actual gain will be less, and that's normal. Now, an interesting thing about output stages is that obviously speakers are not, they don't have a single resistance, they have an impedance curve. So generally speaking, speakers, like for instance, if you're building a guitar amplifier, you're just going to have a single speaker, and the impedance curve will look something like this. All right, so frequency is this way, and impedance is this way, so that's Z, impedance. And so this bit's right here will probably down in the 8 ohm range or something like that. We might come up to 16 or 20 ohms here at the resonance of the speaker, so let's say just 16 or something like that. And then it'll be 8 again for a lot of the operating point of the speaker, but then what it'll do is it'll go right up because the speaker becomes inductive, and it becomes a very high resistance load at higher frequencies. And so what that does is, depending on the frequency that you're doing, you're putting into your amplifier and you're driving into your speaker, the load line does this. And so it might be like this most of the time, and then at speaker resonance, it kind of does this. You know, it straightens out, and you can see, whoa, now we're swinging up a lot more voltage, which is why if you unload a tube amplifier and drive it, you can damage your components because the voltage will swing very high. So maybe you swing up like that, and then you get past resonance, and it goes back down like this, and then the high frequencies go up and your load line kind of flattens out again into those high frequencies. So this is not a fixed thing. This is highly dependent on the load that you're driving with the transformer secondary. So just keep that in mind. All right, the next thing we're going to do is we're going to look at class AB. So this is a single tube. So let's do push-pull. First we'll do push-pull. Let's do push-pull class A, and then we'll do push-pull class AB. All right. There's not much to say about push-pull class A, honestly. It's just 2 class A output stages in push-pull. So with push-pull output transformers, this is interesting and maybe slightly confusing. They are rated plate to plate. So they're really kind of like 2 output transformers. So this is what your push-pull output stage is going to look like. You know, roughly speaking, right? And so you're going to have your grid stopper here, like this. And here is your previous stage from your phase splitter. And so this one looks like this, and this one looks like that, right? They're out of phase. And it's coming in here, and your output transformer looks like this. Like this. And your plates connect here, like this. And your B plus comes in here, your high voltage, right? And then you've got your core, and on the output side, you have your speaker, which we'll just represent with a load. We'll say it's 8 ohms, something like that. Now, the way push-pull output transformer works is they're rated plate to plate. So if you get an output transformer, push-pull output transformer that says 8K, let's say it says 8K, plate to plate, what that means is that from here, from plate to plate, across the entire primary, across the entire primary, is going to be 8K if the output is 8 ohms. Now, if the output changes, like a speaker does, this changes as well, but we just assume that the output is going to be a resistive 8 ohms, and so we also assume that this will be 8K. But the plate, the output tubes don't swing across the whole plate. I mean the whole primary. They only swing across half of it. And so an 8K plate to plate is going to look like a 4K load line. What am I writing here? load line. 4K, I was trying to write a K and then I was saying load line. So it's going to look like a 4K load line when we plot it on our thing here. And the other interesting thing is if you go into class AB, one of these tubes will turn off at some point. And when you apply infinity resistance to an output transformer winding, that's like opening it up. And when you open up an output transformer winding, it acts like it doesn't exist. And so what you've done is you've effectively removed half of the windings from the primary side. And so that changes the ratio of the entire output stage. And suddenly your 4K that you were seeing on each side halves. Well, it doesn't do it suddenly. It does it over a short period. We'll show you in a minute here. But it's going to end up being 2K. So you're going to have two load lines. And you're going to have a transition point between 4K and 2K if your output transformer is rated at 8K, for instance. So now let's go back to the load lines. Here we are. Now, if you're doing a Class A push-pull stage, you haven't got to worry about that. You just take your 8K plate-to-plate or whatever it is you've decided to do, and you can discover what you want by just placing a reasonable load line here, you know, and just sort of figuring it out. And you don't have to worry about transitioning to Class AB because you're going to do if you're doing a Class A, you're going to be biasing, you're going to be setting your output point somewhere up in here. Now, you're going to see in a second here that Class AB operating points are very different. So, for instance, let's do a Class AB operating point. So the first thing we'll do is we'll go up in voltage for our operating point. Let's go all the way up to, 500 volts is the max. So let's do 490 or whatever. We'll start here. And let's just ballpark it for now. We'll do maybe a load line kind of like this, right? Now, we're at negative 57 odd volts here on the grid. And so we can go up 7 segments of 8 here. But we can't go down that far before the tube turns off. It's going to turn off somewhere in this region right here. And so remember, we have 2 of these and they're working in antiphase, right? And so when this one gets up here, the other one's down here turning off. And the point at which it turns off down here, now let's see, 7. So we got 1, 2, 3, 4, 5, 6. So right around the 5 or 6 range of these sort of grid segments, we're going to see the other tube basically turn off. And at that point, remember, your load impedance halves. And I'll show you it's interesting what happens at that point. So let's see, what did we say? 1, 2, 3, 4, 4 or 5. So 1, 2, 3, 4, between 4 and 5. So whatever angle you have, you're going to double that angle. And so your new load line is going to look something like this. Now this is where it gets interesting, because they double. Like let's say your load impedance changes. So this is what they're going to do now. This will go up, but it keeps doubling, right? And so you can see that now we're zipping outside of the maximum dissipation range, which when before we were kind of down like this, so like that. So you can see that it compounds there. That's the other thing. It's interesting. The other thing is that if you bias the amp differently, like let's say you take your DC operating point and move it down here, which a lot of AB amps are biased kind of cool, which is totally fine. But look now we can only go up, what, 1, 2, a couple of divisions. So now the other tube is turning off here, right? And so if our load drops, we're ending up with load lines that kind of start doing this kind of thing, like this. And so you just have to keep this in mind when you're picking your output transformer and figuring out like what's a good primary and what's a good operating point and bias point. It's okay to drift outside of the maximum dissipation if you're just doing it on average less than half of the time. And you can see why this ends up giving you a lot more power, because look how much more voltage and current you're swinging through than you would be in a Class A operating point. And look how much lower your bias needs to be. Before in our Class I operating point, we're biased up near maximum. And now we can bias down here pretty cool, which extends the life of the tube when you're not driving it hard, and allows you to swing through all of this greater area of current and voltage, which is why you have the greater efficiency and power output of the Class A output stage, Class AB output stage, right? So let's see what our actual transformer needs to be, though. Let's go back up to our more sane operating point here. We'll figure out what the primary needs to be for a start. So right now we're at 700 and 130. So this is about a 5K. And then when we transition at, what did we do here? 1, 2, 3, somewhere like here. This is going to be a 2.5K load line. And you could actually chart that out. You could take your longer load line or whatever and make sure that, bring it down here and find your 2.5K, your exact slope or whatever, and then just move it up to the point at which it's going to transition from Class A to Class B. Now, in reality, this is more of a curve and not so much of an immediate transition, because you can see that the tube doesn't cut off immediately. It just gets closer and closer to cut off. And so the transformer gets closer and closer to transitioning from a 5K, this would be a 10K, obviously, because remember this, so we're looking at, this is a 5K load line that then transitions into a 2.5K, but the transformer will be rated at 10K plate to plate. And so if you wanted to go for instance, an 8K plate to plate, that would be 4K and 2K. And so you can see what that would do. It would kind of go up like this, and then this would kind of go up like that, And that's not so bad. You're getting pretty close there. Now, if you wanted, I think this moves up like this because we moved our bias point up. And so we can swing a little bit further before we go into Class A. And I notice that the hotter you bias this, the further your Class A moves up. And so if you biased it hot enough, and this would be, in this situation with this voltage, it would be past max dissipation. If you bias it hot enough, you go straight into Class A again. It never gets to Class AB. So you can kind of see how that works. So it would be like this. You move this all the way up. And this would, once that gets up above 0 volts, that transition point, you never reach it. And now you've got a Class A stage again. And so you bring this down like this, and suddenly you're transitioning in Class AB much more quickly at that point. Hope that makes sense to you. So in calculating the power of Class AB output stages is more difficult because the sine wave from each tube is no longer sinusoidal. And so you can't just do the average voltage by the average current again times 2 for 2 output tubes. You end up with a little bit more than that in the area that sweeps out. And so it's a little bit more tricky. And I haven't found like an equation that always 100% gets you there yet. But suffice to say, your goal with a push-pull AB one output stage is to swing through the most voltage and current that you can. And so if you're trying to maximize power, you're setting your operating point here to swing through the most voltage and current that you can to get the maximum output power. All right, so next, I know this video is getting kind of long, but next let's look at ultralinear curves and pentode curves. All right, so here we go with ultralinear. You can see that the curves look different now. And also the thing to notice about ultralinear is that, so with ultralinear, you've connected your screen on your pentode to a 40% tap on your output transformer. And what that means is that whatever plate voltage swings, the screen swings 43% of that voltage. And what that results in is sort of a halfway between pentode and triode operation. So it still gives you some of the voltage sourcey, low output impedance characteristics of the triode stage, but also, if you'll notice, gives you access to this whole area that we never had access to before. So we can swing lower in voltage and higher in current than we could previously. Previously, we were stuck right in here. And so you can see why ultralinear is making more power now. because we're going to be allowed to swing more and more. And so these just continue like this. Yeah, they get squished down there. So I'm going to save myself the pain of doing the curve again, since it'll be about the same. It's going to look kind of like this. And so let's draw a load line for this. Let's say we're going to do AB1 output stage, and let's assume we're up at I don't know, 400 and some odd volts again. Let's just say our operating point's somewhere in here. So here we go. I'll put my blue tack there. Our operating point is something like 460 volts, and we know it's going to be AB, so we don't want to go too nuts with our initial load line, because we know that somewhere in here it's going to zip up again for that difference. And so let's calculate this. So I assume if these are equal intervals, this out here is going to be what, 55, so it's going to be 610 up here, whatever. So let's just say it's going to be it's going to go up to 600 odd volts up here, like that. And we're going to go to 190 odd milliamps. So we'll do 600 divided by 600 divided by 0.19 equals. All right, so we can see that we've got a load line here for 3K about, and so that's going to be a 6K plate to plate. And we know that at a certain point here, so what do? We can go 1, 2, 3, 4, 5, probably 5 divisions down before we turn the tube off, and so let's go up 5, I guess. So we go 1, 2, 3, 4, 5, and so our transition point to AB, what did I say, 1, 2, 3, 4, 5, it's going to be right in this range, something like that, where it will then double its angle down to a 1.5K. And so you can see we've guessed pretty close here. You know, it might be better to keep it more within dissipation, so we could reduce our load or increase our load, which would kind of shift our load line down like this. Now remember, your speaker though is going to go over a wide range of frequencies. It's okay if it occasionally kind of does this, but you can see we've already ballparked our output transfer. You can see how easy it is to ballpark the output transformer primary impedance or ratio, because we know that 3K here, so that's going to be a 6K plate to plate. Each one's going to see 3K, and it's going to see 1.5K at the transition to class AB1. And so you can see how easy that was. Now look, we're swinging way, way, way more current because we have access to this area now. We're swinging up to like 240 milliamps, and we're swinging down to cutoff basically. So we're swinging 240 milliamps. You remember with our class A, single-ended stage, I think we were swinging 80 or something like that. So you can already see, and we've got 2 tubes now instead of 1. And so you can see how much power is now available with ultralinear versus triode. Now, what the price you pay for that, if you calculate the plate impedance, which we did on the previous stage, which I guess I'll just go ahead and do again, the difference between 150 and 220, so 220 minus 150 equals, so to change the plate, 70 volts we need to source. The difference between, we need to source 30 milliamps, so we'll divide this by 0.03 equals. And so you can see that our plate has gone up from, what was it, 1.8K to 2.3K output impedance. So that's the price you pay for the greater power output. But still, that's not so bad. So you can see why ultralinear is a good sort of compromise. All right, so next thing we're going to do is we're going to look at pentode curves. All right, so now we finally get into pentode land here, and you can see that the curves couldn't be more different. When before they were sort of voltage sourcey, kind of coming up like this, now we're in current source land, where you basically have a pure transconductance that ignores the plate voltage to a large extent, and only gives you a current out compared to your voltage differential input. So let me just really quick draw our load line again, or I'm sorry, our dissipation line again, looks something like that. That's probably wrong, but you get the idea. You know how to do that now. And but you can see, like, look now we have access to this area over here we can swing through. So if we're going to do in class AB output stage, we could pick our operating point. I guess we don't want to go above our max for our... So obviously this is, so pentode operation, you connect the screen grid to a fixed voltage, in this case 200 volts. And I think that's in the data sheet. So there you go. This is what the curves for a 200 volt screen grid 6L6 looks like. And we can pick an operating point here. We know we're going to go AB, so maybe we should pick a lower current here. That way we'll go to AB a little bit sooner. So something like, maybe even like this. And then we know that when we go down, so we go down a few here, these continue obviously, and you go up a few, we're going to transition to the class AB right there. So now we can figure out what our sort of our load should be, our plate-to-plate load, and our half of that is this guy, and a quarter of that is this guy, just like before. And you can see that we're making more power now because we're swinging more current and we're swinging more voltage. And I think as a general, they like you to go through the knee is what they call it. And so you can sort of adjust these so that you swing all the way up to this current, but also all the way down to this voltage to get your maximum power out. So your load line is going to look something like this. You can calculate what your output transformer should be. You can see your operating point here is going to be between, it's going to be about negative 22 volts between the grid and the cathode. You're at about 500 volts on the plate. So yeah, everything is looking good here. But let's talk about these pentode curves and talk about plate impedance. Now before we went up from like 1.8 to 2.4K or something like that. But if you look at the plate impedance of a pentode, it's very much higher than that. And so you think, if I'd like to change, for instance, let's say I'd like to change the voltage of the plate by, what is this here? It's very difficult to determine now because the curves are so slight. And so let's say I want to, so the difference between these is 15. So this is about halfway, 15. So this is 15 milliamps, and it's the difference between 600 and 225 volts. So 600 minus 225 equals, so we're going to change the plate voltage by 375 volts. But to do that, we're only going to need 15 milliamps. So we'll divide this by 0.015 equals. So look, our new plate impedance is 25,000. All right, and so remember how a perfect current source would have an infinity output impedance. Well, this isn't infinity, but it's getting up there. And you can see that now the voltage gain of the tube is no longer really that interesting. Now the primary sort of factor of the tube is its transconductance, because the plate voltage no longer really changes the conductance of the tube that much. It's all about the differential between the voltage differential between the cathode and the grid. And so that's pentodes for you. And the way that they accomplish this is basically the cathode and grid system only see the screen voltage. And so the plate can swing around without affecting the electron beam that's going through to arrive at the plate. So that's how that works. Anyway, I know this has been really long, and if you've made it this far, good job. I hope this has illuminated plate curves and load lines and output stages and driver stages for you. And thanks for watching.